So, good morning, all. Probably we'll give a couple of minutes for others to join as well. And I also noticed that there is a little bit of lag from the live streaming as such. So, in case of any questions, please do share it across in the chat window so that I can respond to you shortly. So, we shall start the session. Very good morning. And um, my name is Prasanna, as you all might already know. And in today's discussion, what we're going to do is we're going to look at uh, where we are currently in the artificial intelligence world and what is the goal of artificial intelligence. And in terms of artificial general intelligence, what are all the different approaches and how we can actually reach towards it, and what is the right way to reach there. So that is the whole goal of today's session, and we will be talking about uh, different approaches that are being done in the AI world. Before let I start, let me just give take a small scenario and understand what is the current approach followed in terms of artificial intelligence and where we need to go. Let's take a simple scenario, like let's assume that an XYZ bank wants to build a AI ML model to automate their loan applications approval or rejection process. If you take this simple scenario, as a data scientist or an ML engineer, how do you actually approach the whole problem as such? Right now, the approach followed is as is. Now, the first step in the whole process of building this AI model for accepting or rejecting your loan application, the first thing that you will do is go to the bank and try to collect all the past data specific to the loan application, specific to on what basis they have accepted or rejected the loan. And the first process is in terms of collection of the data. And once you collect the data might be in different format, and the data might require a lot of fine tuning and correction. And you basically clean and process the data and make it ready for AIML. So this is typically called as exploratory data analysis, where in this EDA you basically understand in deep on what is the data that you received, how do you make it ready, available, and suitable for your AI ML model. And once you have the data available, you apply various machine learning algorithms and try to find what is the best suited algorithm that can be taken for next step. Once you identify the best model, the next immediate step is using that model, build an using that algorithm, you build a model and make it available for production. And the last step in the whole process is you deploy this model in the production, so that using this new model, the bank can actually start approving or rejecting any new loan application that that receives. So this is a typical steps that has been followed in any um AI applications as we speak. So this is the current stage of AI as we know it. So now, what is the um, shortcoming in this approach? If you look at the first shortcoming is in the case of the model that you have spent a couple of weeks or months to build has only one purpose. It has a very low usability where you can use that model only for that particular problem that you have defined for. Now, in this case, you have defined this model only for your loan approval rejection process, and you can use that particular model only for that particular problem. Now, suddenly, bank comes and say, "Hey, you have created this model for this loan approval rejection. Can I use it for some other department, for some other purpose?" And it cannot be used at this stage. In case uh, the data that you used for this particular model, if it changed, or the features that you have used for building that particular model, if any change happened this in this particular model that you have taken, the whole model goes for a toss. Basically, the whole model fails. And the second thing is, the model basically utilizes your data that you have created in terms of from the bank, and it utilizes only the data for building that particular model. And even any change in the data that you have received, that model is going to fail. So does it mean that is it an intelligent model? It is not that much of an intelligence that we can see. And the other problem is, when the particular model predicts whether a particular loan can be accepted or rejected, it does not give you how it has come to the actual conclusion. You build the model, and if certain criteria are met, it basically accepts the loan application. If not, it's going to reject. So what is this criteria that particular model uses for accepting or rejecting? That information is not known to the users who are using it. So if you look at the current stage of AI, it is pretty much artificial narrow intelligence, because it is very narrow in terms of the actual problem it is trying to solve, actual solution it is trying to come out with. So then, if it is narrow intelligence, then what is the goal of AI? So the goal of AI as we know it is to move from the narrow intelligence that the model has to a general intelligence where it can be at par with the human intelligence that we have. So as a human being, you can multitask. If I want to go for a shopping, you can identify different product. You don't need a different brain to actually work out at a shopping mall. If you are going for a theater to watch a movie, you don't need a different model to actually understand the actors what they are speaking. So effectively, you have a single brain where it can actually segregate different things that are happening in the world. And the goal of the AI is to go from the narrow intelligence of each model predicting only one particular activity to a general intelligence where a single model can be used for multiple purpose. And if you question, is that the goal, we can even push the boundary little further. We want the AI to go beyond human intelligence. Even if you look at human intelligence also has certain restriction in terms of what is the max that it can do, but with a proper training we can actually expand that particular intelligence and allow the artificial intelligence to go beyond the general intelligence and go reach a super intelligence level. So that is our pretty good goal in terms of AI as such. So to understand where we are currently in the actual cycle, if you look at the current improvement and the advancements that we are seeing in the market, we might be somewhere here in terms of where our AI is currently. Now, where we need to go, we have a long journey to do, where we may have to go from artificial narrow intelligence to a general intelligence and go beyond the general intelligence to a super intelligence. We are nowhere near to human intelligence yet. We are still in the research phase, right? So, so now specific to the specific to reaching the artificial general intelligence. So, what are all the different approaches that are being followed? And in this section, we will have a look at what are those approaches and how we can actually utilize those approaches for moving towards artificial general intelligence. So let me detail that. So the first approach is evolutionary computing, and the second approach is symbolic AI, and the third is a graph AI, deep reinforcement learning, and Bayesian network, and quantum computing. These are some of the approaches by which various research are in progress in parallel to push our boundary from artificial narrow intelligence to artificial general intelligence. Right. So I will not go in deep on the programming perspective, but at a high level, let me explain all these different approaches that are going to help us to reach AGI. That will give you a brief about how we can actually reach AGI. So, so let's start with evolutionary computing. What is this evolutionary computing? We all human being knows the fact that we have evolved from a longer period of time, and we have reached the intelligence level currently we are holding currently. And in the evolutionary process, the science of evolution has given us some of the basic principles that has guided us to reach where we are currently. So the base of the whole evolution, we can consider a chromosomes, and how these chromosomes have evolved, and the genetic process of human being has evolved so that we have achieved to this level. If you do not understand, don't worry about it. Let's see some examples so that you will understand it shortly. Right. So the basic principle of how we have gone from a monkey to a human being has happened. There is a basic principle of genetic mutation. The genetic mutation, the basic chromosomes which are available in the body has gone through transformations, and this transformation enabled us to reach where we are currently, right? So to go to the next level of understanding how these mutations happened, let's try to understand what are all the different type of mutations And what is meant by a crossover? A mutation as such, for example, assuming that this is a chromosome, and a mutation process of deletion, if I wanted to understand, in the chromosome, delete a portion of a chromosome and come out with a new chromosome in the new generation. It is like from your father, some of the features and the capability that you inherit from your father, likewise from your mother, you might have inherited some of the features and the capability to your self. So that is, it could be a deletion where some of the features of father could be deleted, and in the new generation, you, if you consider you as a new generation, how you have brought in some of the features of your father, or there could be a certain capability which is duplicated in terms of duplication, where the same capability is duplicated in the new generation twice, or inversion, where the capability is inverted and a new capability gets inserted, where a different type of chromosome gets inserted into the particular chromosome that we have. In this example, chromosome 4 is inserted with chromosome 20 to build a different type of chromosome, effectively at a very base level. And these are different type of mutations. Let's look at a crossover. So you can consider the crossover example of a parent and child. Some of the capabilities of parent, let's say a parent A and B, and when you have a child, and some of the characteristics of A and some of the characteristics of B will get created, and the new generation is formed with a new type of characteristics. So these are some of the of basics of our evolutionary theory. And in this, we are talking about generation. Effectively, we all know that what is a generation in terms, you know, we call it the generation Z, millennials, generation X, as we might have come multiple generations. After multiple generations of evolution, we are currently where we are now. So the whole genetic algorithm or the evolutionary algorithm can be represented in a simple way like this, where this basically represents a single generation process, where from a group of items you do a selection, and the selection is nothing but from the actual list of features which are there, you do a selection, and from the selection you apply a crossover, apply a mutation, and when you apply a crossover and mutation, you brought in a new generation, and you evaluate whether this new generation is actually uh, what you are expecting. And if it is not, you go back, basically repeat the whole process. What you are currently seeing in the screen is a single generation, assuming that the same process repeats for multiple generation. And as things move, there is a saying like, um, uh, effectively, um, the survival of the fittest, and the survival of the fittest basically survives and thrives in the whole generation process. So this is what the evolutionary algorithmic process is called, genetic algorithm. So the genetic algorithm starts with randomly generating a population and evaluates the individual, and it do a selective reproduction, apply crossover and the mutation, and see whether you have achieved your target, what you wanted to achieve. If not, you continue to repeat the whole process. if you achieve the best outcome that you are expecting, then you basically stop the whole process and provides a result. That's how the human has evolved, right? And apply the same for a computing problem is what a genetic algorithm, where for any problem that you are looking at, how you can actually apply genetic algorithm and iteratively perform crossover mutation and perform multiple generations of cycles and to achieve the best outcome. There are many mathematical problems which were not possible to solve using a typical mathematical outcome, were able to be solved very easily and beautifully using genetic algorithm. So it basically uses the concept of a chromosome mutation and the crossover and the generations to actually come out with the best outcome. Nothing but it utilizes the survival of the fittest to actually come out with the best outcome, right? So that is in terms of genetic algorithm. Here is an example of how the genetic algorithm actually evolves as the generation goes. So this is an experimentation done where individual the person walking is the simulation that is being taken up uh, for the simulation. And here, as the generation goes, the actual walking is consistent and we're able to achieve a better result. And similarly, the genetic algorithm walker is an example of how applying the genetic algorithm helps make a perfect walk as the generation moves further. So here, there is no hard and fast rule on how many generations that you need to actually evaluate for getting the perfect outcome. All these are, given to you, where you can apply your own selection process, your own approach of how many generations that you wanted to actually iterate to identify the perfect outcome, right? uh, because there is a concept of crossover and mutation, and this crossover mutation and the natural selection of survival of the fittest is being applied, we may not be able to accurately reproduce the same outcome that you might have received from each and every generation um, iteration that you are doing. For example, if you are building this generation genetic algorithm walker on the first round, assuming that you are using around 2000 generations to actually make the particular image walk properly. Now, the second time when you wanted to actually bring in the same kind of an outcome in the same 2000 generation, it may or may not be as equal to what you are expecting. So that is one of the shortcoming because of the actual crossover and the mutation and the natural selection of survival of the fittest are being happening in the process. That is the reason that it may not be possible, right? So the advancement in the evolutionary algorithm is neuroevolutionary algorithm, and there are research papers which are talking about how Google has utilized this neuro evolutionary algorithm along with the neural network so that they could actually come out with a better outcome on the neural network prediction as such. So now we looked at evolutionary algorithm. The next solution is in terms of symbolic AI. The symbolic AI provides an interesting approach to actually look at the problem. The evolutionary algorithm looked at mimicked how the human evolution actually happened. The symbolic AI basically mimics how human brain basically works. In the sense, when you look at a physical object, we will be looking at these object assets. In the sense, when you look at a chair in an office room, you understand that it is a chair. You will not go into the details of it has three wheels, four wheels, and it has leather or the details. You look at as a chair. From a machine point of view, things are being looked at in zeros and ones. Instead of representing things as zeros and ones, how about representing things as symbols? Is the actual premise of symbolic AI. Like human sees things as chairs, objects, persons, laptops, and etc. In the symbolic AI, basically there are logics are being defined to solve the problem. Symbols are the one going to represent the problems in the computers. There is something called a knowledge base, which is going to be having a huge set of symbols and their relationship. What is this relationship? For example, let's assume person as a symbol, bread as a symbol. The person basically eats the bread. So there is a relationship of eat is to represent the person basically eats the bread. Similarly, there are many logical connections are being defined. For example, the person can eat and we can eat the bread, and the logical connection of and can also represent a person can eat and we can eat the bread. The logical connections for people with a programming background, this is much similar to uh, your operators, that your logical operators that you are using as part of your programming language. Similarly, implications, which is similar to an if then statement that you use as part of your programming language. So if a person is hungry, then he eats bread. So this is how basically the logics and the symbols are used to represent the complete knowledge base. The outcome of a symbolic AI, or the process of symbolic AI, is defined by knowledge base. The knowledge base represents all the knowledge, uh, and their relationship and the implications are all being represented in the knowledge base effectively. So there are many advanced use cases in terms of voice assistants and chatbots are performing much better even when you compare to a neural network based chatbots and the voice assistants. In this case, the first thing is you need to have a huge knowledge base, and that combines various symbols and their relationship so that you can get a voice response from them. Okay. And advancement in the symbolic AI is called neurosymbolic AI, where in this neurosymbolic AI, we basically combine the neural network with the symbolic AI for representing the details. Now we looked at two different solutions. The third one is in terms of graph AI. Now, basically, when we talk about any complex relationship, it is not just the attributes which are important, but the relationship for that attribute is very, very important. For example, in this diagram, you see a user is there is a tweet. Effectively, the relationship between the user and the tweet is what is the actual activity that he has done. User basically posted this particular tweet, and this user, there could be multiple user, And in this tweet, there is a mention of a user in this tweet. Now, here, there is a relationship that actually represents what is happening there. But in a typical machine learning models that currently we are building, you typically take the data in a tabular format, and you apply the machine learning model on the tabular format and try to come out with a prediction for typical logistic or linear regression and so on and so forth. Okay, I'm not talking about image or voice based one. I'm talking about a uh, typical logistic or linear regression based models. Now, what is the problem in this approach? We typically tend to ignore the relationship while we are performing the operation. We typically focus on attributes, and the relationships are not normally looked at. But relationship plays a very important role when it comes to come out with the proper predictions and come out with the proper outcome as such. And that is where the graph play a very important role. The graph based machine learning model can actually transform the way the AI currently works. Now, not just the nodes but also the relationship actually can bring in lot of intelligence when the predictions are happening in the graph. Now, but the graphs are a complex structure where you have nodes and the relationship. In some cases the relationship directions can also play a major role. In the example that we have shown, the twitter the tweet the tweet, there is a user who is actually posting a tweet, and there is a user who is actually mentioned in the tweet. So the direction of the actual graph also plays an important role. So how do we actually apply machine learning algorithms in such scenarios? There is a new set of graph embeddings are an approach to actually solve this problem. And you can actually take the graphs and apply graph embedding. And once you apply the graph embedding, and you can typically utilize the normal machine learning approach like neural networks or linear regressions and so on and so forth for your graph based solutions as well. Now now apply the graph embedding, the outcome of the graph embedding, apply the graph neural network or graph machine learning and so on and so forth. So that is possible. Now, there are various libraries which are already available, which are prominent. And what I am showing in the screen is only a glimpse of it, where there are lot many are available in the market. The one that I am showing is predominantly a open source one. For example, Neo4j is a graph neural network. DeepMind has GraphNets library, and deep graph library is also used for your graph based machine learning algorithms. There are other proprietary solutions. For example, Tiger Graph, which is one of the prominent graph based machine learning algorithm provider, uh, which can actually perform a much better job of graph based neural network and machine learning processing as such. So that is graph based approach. And the next approach is deep reinforcement learning. Deep RL, the reinforcement learning as such, works in an agent environment relationship. The agent environment relationship. This diagram very beautifully depicts how agent actually works, and how the agent actually interacts with the environment. Okay. Now, basically, agent is going to perform an action, and when he performs an action, based on the action on the environment, he will get a reward. He will get a reward, and the agent will absorb the reward, and based on which he will take the next action, and repeat this for very many times, as many times as you wish, so that you get a proper outcome. Here in this case, where the environment is nothing but a owner basically throws a stick, assuming that the dog as an agent performs an action of grabbing that particular environment, nothing but the stick, and coming back and giving to the owner. And at that time, the owner could give a reward of some small food. Now, the owner gave the food when the dog basically grabs the stick and given to the owner. So that is an action that it has done. That is a positive action, and the positive action has given a positive reward for him. Now take the negative action. For example, when the owner throws the particular stick, the dog does not do anything. It just simply watches, and in that time the owner could actually make that particular dog to actually go and grab. Here is the reward is the owner is actually criticizing the dog to actually go and pick the stick. So it absorbs the reward. It is a negative reward that it got. It did not get any extra food or snack or something. So now the dog understands that if it picks the stick, it gets the snack. So next time when the owner throws the stick, it the dog, the agent basically takes the action of grabbing that particular stick and giving to the owner, and it gets a reward. It is a positive reward. Now dog understands that as long as I grab the stick, I get a positive reward. So as long as I get the positive reward, I repeat the whole process as such. So that is the iterative reinforcement learning process. Now the same reinforcement learning can be applied, can be translated into a programming, and can be applied. So that is the approach of reinforcement learning in machine learning world. And we see lot of AI winning lot of games. It could be chess, go, and there are so many games that you might have seen. All are being owned by AI. All are done with the help of reinforcement learning. And the advancement in the reinforcement learning is called deep RL, deep reinforcement learning, where they apply deep neural network uh, for the actual reinforcement learning. And one of the algorithm which is much famous is deep q learning. And deep q learning is the latest and greatest in terms of deep reinforcement learning as such, right? I'm sure most of us might have seen this image where a robot basically walks and dances, and even some other videos where we could see it fights with people and so on and so forth. And Boston Dynamic typically utilizes the reinforcement learning for training these robots for their actions as such. So this is deep reinforcement learning. Now, the next approach is Bayesian network. Now, the Bayesian network follows an approach of utilizing the probability, especially a conditional probability theory, and apply it on a special type of graph. And this basically has given a lot better outcome in terms of computing as well as the actual prediction outcome as well. So these type of networks are called Bayesian network, And the outcome of this, utilizing the Bayesian network, applying the neural network, were called Bayesian neural network, right? So the special type of graphs are called directed acyclic graph. The directed acyclic graph represents the graphs will have a mandatory direction in place, and acyclic meaning there won't be any cyclic details available in the graph. The reason for such graphs are they are best fit to represent a conditional probability representation, and these conditional probability representation can actually perform much better in terms of identifying solution to a problem, and utilizes the probability theory, and the advancement in this field are called Bayesian neural network. And now the last approach that are being followed are quantum computing. Now quantum computing were there for many decades, and application of programming and the machine learning has actually taken this to a very new level. Now quantum computers has a special type of bits, and these bits are represented by something called qubits, and the qubits at a specific temperature or the actual position, which is called a superposition, it generates a special type of feature called superposition. And in the superposition, basically each and every qubits can represent both a 0 and 1 as the outcome, meaning the qubits basically can be at 0 or a 1 state at the same time in the superposition state. This is a very unique scenario whereby many of the complex problems that may require millions of years to solve can be solved using quantum computers. And there are many companies are in the forefront when it comes to quantum computing and the machine learning as such. The diagram talks about some of the leading one. D wave actually leads the um, whole whole quantum computing way, and IBM has taken this to a next level. Their solution called Qiskit. Qiskit is the kind of a software development kit for working on quantum computers as such. Qiskit, which is an open source library for enabling anybody to actually go and experiment on the quantum computers as such. They provide quantum simulators. Even they allow you to actually access their quantum computer remotely from your machine to experiment on these quantum computers as such. So that represents all the different approaches that are currently being followed for achieving what is called artificial general intelligence. Evolutionary computing, symbolic AI, graph AI, deep reinforcement learning, Bayesian network, and quantum computing. So, what I have represented is only a glimpse of some of the leading research. There are many other research which are going on in parallel, which I have not covered, and those there are a lot more research which are going on in terms of you know reaching towards artificial general intelligence as such, right? So, this gives you a overview of what all the different approaches with which the AGI research is going on. So overall, if you look at the current perspective, the AI as such, we can look at classifying by using data. For example, If it is a vision based data, your actual approach and the algorithm that you use for vision based problems are completely different. If it is a speech, it is a completely different. And text, time series, these are some of the classification of, based on the type of data that you are using, the actual approach to actual artificial intelligence is completely different. And the second differentiation is in terms of algorithms. Whether you are using a supervised algorithm, unsupervised algorithm, whether you are using reinforcement learning or deep learning, or it could be any of the items that I have mentioned in today's session, or any of those could be a different type of algorithm for solving your problem as such. It could be a process actually. You could be doing a multiple way of cleaning and labeling your data. There is no one hard and fast rule, and there could be multiple way of performing feature engineering and training and inferencing your data. And and not just that, there are different domains brings in a lot of different challenges, healthcare being on the top, where the complexity is much much higher. Healthcare, telecom, retail, government, there are a lot more uh, you know uh, streams and the verticals which can actually have much more impact on the AI and machine learning as such. So you could choose, if you are choosing a vision, then you could choose a different algorithms for the particular vision specific data, and you could follow a different process, and this could come under a different domain as such. So these are different perspective on how you basically achieve the machine learning. So taking a step back, so let's take that, assuming that you're all doing all this, but all the approaches that I was talking about, do we know the fact that how the AI model actually works? Do we really understand how the AI predicts? That's a very basic question, and this is allowing me to take the step back and look at even all the approaches that we are talking about, the different quantum computing, or could be deep reinforcement learning and so on and so forth. Do we really know how the AI actually predicts? That's a very basic question. So there is a interesting research done by some of the researcher. From their research paper, I've taken this. What they have done is uh, they have they have taken a neural network model, and this neural network model is basically to classify images and identify the actual item which is in the image actually. And this particular model actually classified guitar with 98.9% accuracy and penguin with 99.9% accuracy, which is a very high confident level that it is able to predict this deep neural network model. Now, what these guys have done in the research is they have applied a specific type of noise in the actual model and the actual image that they have taken. And this is a noise, and this is an image that they have taken. And these images were classified as guitar and penguin perfectly by the same model with 99.99% accuracy, because they understood how the machine learning model worked. They were able to very easily trick the model to actually come out with a false outcome. So what this experiment represents is the confidence is not good enough. The model's confidence level is not good enough for your actual outcome as such. So then how do we solve it? So if you take the current approach followed by many of the artificial intelligence deployment, this is what happens. So the first step is just got some data, let's feed into the neural network, and it typically takes forever to train. But let's wait, it may come out with a good result. And when the magic happens, when you wait and watch. Typically, the AI model is complete black box. You have absolutely no clue what is happening, and you suddenly get a 95% accuracy on the data that you have got, and you are super happy, super excited, and you take it to the production. And some of the basic question is, can we trust this model? How does it predict the situation? And does it actually predicts tells how it actually predicts a particular outcome? All these are very important question when it comes to some of the sensitive domains like medical domain. For example, if you are using, let's say, an AI model in a medical domain, accuracy alone is not enough, but we need to see whether it is giving proper outcome. It can be used as just as a reference rather than actual decision making as such, right? So the problem with the current AI approach, the regulators also understood there is a serious problem. That's where, if you look at the Information Commissioner's Office of UK and the GDPR Act, actually, uh, given the fact that all the individuals should be given information about automated decision making process in terms of any decisions are being done or made. It could be, let's say, you apply for a loan and it got rejected. There should be a clear explanation of on what basis the rejection was done. So that is a mandatory step that has been provided there. Similarly, the US government has come out with something called, um, the organization should constantly assess the machine learning models for biases and frequently perform corrective actions. That's a mandatory step that they have mentioned. Similarly, European Union has given a right to explanation act where the user can ask for an explanation behind the decision that are being made, right? So these are some of the regulatory specific progress that are being made. Now, why it is important to understand how the AI model works? The reason, the first is the technology development. If you take the recent neural networks that are being used for the machine learning models, it is literally impossible for us to understand the number of layers, the complexity of the layers, and the complexity of the calculation that are happening in the actual machine learning model, where humongous that it is literally impossible for a human to understand what is going on behind the screen. Even if you wanted to understand, you can understand at a very high level, but how the prediction happens, it is literally impossible to understand it. So that is where in the recent years, maybe from 2016 onwards, there is a new field of explainable AI has been pretty famous. Now, why we need an explainable AI? Whenever a particular model, AI model that you have built is providing an outcome, you need to justify on what basis that particular model has given that outcome. Because you have a justification, you can actually control the model's outcome and improve that performance of the model. And even you can go and improve and discover new inferences from the model outcome. So these are some of the need for an explainable AI as such. Uh, so does it require to apply explanation on all the AI models? So should we actually apply explanation on all the models? It may not be the case. It is not necessary. So in the case of, let's say, an advertisement, you are building an AI model for an advertisement. So the AI model is going to give you a certain type of advertisement for certain category of users. And even if the particular AI model is giving a wrong type of advertisement to the user, it is not going to impact much. It is not going to have much of an impact for that particular user. But let's assume that you have an AI model that is used for, say, healthcare, legal, or military purpose. And these particular areas, the AI model gives something wrong. A person who does not have a cancer, and the AI model predicts and says he has a cancer. That's a very serious problem. And in such scenarios and in such use cases, it is mandatory that you provide a detailed explanation of why it happens, what it happens. So that is very very important there. So there are various ways the explanation can be classified. The explainability can be classified. You are building an AI model. The AI model is a complex model, very complex model, where it has the neural network with 100 different layers and the 100 different neurons that are being used for each and every layers. Then that is a very very high complex model. Or there could be an AI model that you are building which has only two layers and two neurons. It's a very simple model. It's a low complex model. So the complexity based explanation is one. The second is scope based. So do we you have an AI model and it does a prediction. Do I need to explain about the outcome of the prediction alone, or do I need to explain the whole model itself, how the model actually works? So these two are two different things. So do I need to explain about individual outcome of a prediction or a complete model itself? That's a two different thing. And the third is the level of explainability. The level of explainability provide the explanation for specific set of features or the outcome that you are looking at, or you want to explain in detail in clear English why the prediction has happened, or just provide what features are affecting for what. Okay, so that is what are all the different ways in which the explainability can be classified. This is just the very high level, but there are so many other approaches and the ways with which you can actually classify. Let's look at some of the frameworks which are available and how these frameworks can actually help on the explainability. So, for example, some of the prominent one which are open source I have taken. There are very many proprietary ones are available which I have not included here. All these are from large players and open source one. And Microsoft has something called Interpret ML open source framework, and IBM has something called AIX 360 open source, and the GitHub links also provided there. And let's look at IBM's explainability approach. So in the case of IBM explainability as such, the diagram talks about whether the explanation is at a global level or at a local level, and whether the explanation is post hoc or pre hoc based, before the actual prediction or after the prediction as such. And is it a direct explanation or the explanation of the data? So these are multiple ways with which the explanation can be done in the case of IBM AIX 360. There are various different algorithms are being defined in the AIX 360. Based on the type of explanation required, you can utilize that particular algorithm. In the Microsoft interpret ML approach as such, there is a typo on the Microsoft. So there is the classification is based on what type of data that you want. Is it a tabular data? Is it a text data? Is it an image data? There are different algorithms can be applied based on the type of data that you are using for the actual prediction as such. So SHAP is one of the prominent machine learning uh, explainable algorithm. Lime is also another prominent one. Let's look at some of the individual algorithms as such. So some of the prominent algorithms which are used are Lime, SHAP, Elify. All are available and the GitHub links are provided there. So different one utilizes a different approach of explaining how the model actually works. Let's look at one by one. So Lime approach of explaining the machine learning model. Assuming that you have a model and you have a data and a prediction. The model is basically predicting whether it has a you have flu or not based on various data that you feed in: age, no fatigue, headache, weight, sneeze, and so on and so forth. So now assuming that you if the model predicts that you have a flu, then what are all the feature actually contribute to the prediction of whether you have a flu or not? That is what is identified by using Lime. Now Lime basically says builds an explanation model, and this explanation model provides what are all the different features has a positive impact on the actual outcome, and what are all the features has a negative impact on the outcome. Here in this case, the green sneeze and headache were having a positive impact on the outcome, and no fatigue has a negative impact on the outcome. That is, you have flu. That is what is done by Line. So how does it achieves it? Assuming that this is the plane which is your machine learning model's outcome. Now in this machine learning model's outcome space, assuming this is the prediction of your machine learning model, and the Lime will try to actually do a linear regression on the outcome based on the outcome, and all the different features which are near to that particular outcome are considered the influencers of this particular outcome. All the features which are near to the actual outcome are considered the influencers of the actual outcome as such. It could be a positive influencer or a negative influencer, and so on and so forth. So that's an approach by which the Lime actually works. Okay. So the next is SHAP. The SHAP basically follows a game theory based approach of allocating a number called Shapley value for each and every features of a model. For example, let's say I have a model and this model has multiple features, and these features, each and every feature is going to be allocated with a Shapley value. The value gets calculated based on the position and the impact of this particular feature in the whole model as such. Okay, and this Shapley value will help on identification of the what is the influence of the actual feature in the whole model's outcome. Here is an example, here is an explanation. For example, if the output is zero point 0.4, just for an example I've taken, now here the age has had a 0.4% Shapley value positively impacted, and the sex basically has minus 0.3% negative impact on the whole outcome, right? So how the actual sharp value gets calculated, that's a game theory based approach. A beautiful research paper is being published by the sharp team, and that talks about how the actual calculation actually done, the Shapley values are calculated. So these are some of the prominent one which are currently in the market as such. So from my point of view, if you look at now, you could be having multiple variety of AI models, AI algorithms, and also AGI algorithms. The AGI approach, whatever that we are doing, doesn't matter if we do not have a proper explanation of how the model prediction works, how, on what basis the actual prediction works. If we are not having an explanation, doesn't matter whether it is a simple model or is it a complex model, doesn't matter. And all of them should have a proper explanation, should be in place. That is the only way that we can move forward in terms of reaching our AGI, artificial general intelligence, or ASI, artificial super intelligence. And that is the conclusion that I make. It is from my point of view that only with proper explanation of how the AI actually predicts, we will be able to reach where we wanted to reach. That's what I wish to actually share it across on today's session. And I also wish to share my next plan. My next plan, the next workshop, I will try to have a detailed session on artificial general intelligence with the code demo for various solutions that we have looked at, and it will also be LinkedIn event, and you can enjoy uh, you know having that session attended. And if you have any questions, I'm happy to answer any questions in the LinkedIn comment sections. You can post the comments. I'm happy to answer. And that ends the current session for today. Thank you all very much for listening patiently. I hope you have learned something, you have enjoyed something new in the whole process as such. So, thank you very much, team, for your patience and listening to me. And if you do not have any questions, I am happy to end the session. And please reach out to me for any queries or clarification. The email and the contact details are mentioned here. Okay.